Good morning to everyone. Today we are going to see an important relation in thermodynamics, that is Maxwell's relation. So Maxwell relations are derived in order to understand relationship between various thermodynamic properties of a system. So it is derived by James Clerk Maxwell in the 19th century, and it has wide application in various fields of science and engineering. To understand why we need Maxwell relation, imagine yourself climbing a mountain. So when you are climbing a mountain, as you ascend upwards towards the mountain, the temperature decreases and the pressure drops. So the change in temperature and pressure affects the work done in lifting your body. That is, you have to put more work towards lifting your body to a higher altitude. And the heat transfer between your body and environment also is affected due to the changing conditions. So the Maxwell relations can help us understand these relationships and predict how a system will change under different conditions. So when the working conditions differ, how functioning of system can be predicted, can be done using Maxwell's relations. So the Maxwell's relations are primarily derived using 4 different thermodynamic potentials. So that is internal energy, total energy of system, including kinetic and potential energy. That is called as internal energy of the system. Enthalpy, the sum of internal energy and product of pressure and volume of the system. Helmholtz free energy, the internal energy at constant temperature and volume. And Gibbs free energy, enthalpy at constant pressure and temperature. So first we will see how we will derive first Maxwell relation using internal energy. So this is the first law of thermodynamics. It's nothing but rate of change of heat is equal to rate of change of internal energy and work. So rate of change of heat divided by temperature is change in entropy, and heat can be written as temperature into change in entropy. And rate of change of work is nothing but pressure into change in volume. So I have rewritten a statement using these two relations are incorporated in this equation. So TdS is equal to du plus PdV. Now I have to write an equation for du. So du equal to ds and dv. So when you see, you are having two different changes, that is ds and dv. These are the changing potentials in this equation, ds and dv. So when I write the equation, so I will say how we are writing this equation for one equation. So you will understand yourself for the rest of the 3 equations. I am going to write for one equation. So ds and dv are variables here. So here it should be constant. So s is constant here and v is constant here. So when s is constant, the variable is v. So you are having 2 variables, s and v. So on the left hand side, s is constant. On the right hand side, v is constant. So you will have, when s is constant, v will be the variable. And when v is constant, s will be the variable. And you are having a minus sign here. So you should put minus sign at any one of the sides. Okay. So now I have to write dou T divided by dou V. That is dou T divided by dou V at constant T to V. So dou T by dou V at constant entropy is equal to, I have put minus sign here. So dou P by dou S at constant volume. So this is the first Maxwell relation. Let's see for yourself. So dou T by dou V constant entropy is equal to dou P by dou S at constant volume. So this is the first Maxwell relation. Second relation using enthalpy. You know that enthalpy is U plus PV. Now to get dH, we have to differentiate this term. If you differentiate, this U will be du. When you differentiate PV, PV can be differentiated. So the differentiation of PV equal to PdV plus PdP. Now, from the previous slide, the value of du, that is TdS minus PdV, should be incorporated here. TdS minus PdV plus PdV plus PdP. Instead of du, we have put TdS minus PdV here. So dH equal to TdS plus PdP. So when you write, you have two variables here also, that is ds and dP. So both are positive, so there will not be any negative sign. ds and dP. So constants will be S and P. So when S is constant, P will be variable, and when P is constant, S will be variable. So dou T by dou P at constant entropy equal to dou V by dou S at constant pressure. So this will be the second relation. You can see it for yourself. Dou T by dou P constant entropy will be equal to dou V by dou S at constant pressure. So this is the second Maxwell relation. And third relation using Helmholtz free energy, that is F. F is equal to U minus Ts. So when I differentiate this, U will become du and Ts will be TdS plus SdT. Since there is minus sign here, it will be minus TdS minus SdT. Instead of du, here also instead of du, we are having, instead of this du, we have substituted TdS minus PD. The final equation will be dF equal to minus PdV minus Q. So we are having minus sign on both the sides. We will write the Maxwell relation for this thing. So we will have minus sign on both the sides. So there is minus sign on both the sides. So eventually these minus will be cancelled against each other. So this minus and minus will get cancelled. We have two variables, dV and dt. So V and T. So as usual, I already said, when V is constant, T will be variable. When T is constant, V will be the variable. So dou P by dou T at constant volume will be equal to dou S by dou V at constant temperature. So that will be the third equation. Fourth equation will be using the Gibbs free energy. That is G is equal to H minus Ts. So dG will be dH minus TdS minus SdT. So dG equal to TdS plus PdP. Instead of H, I have substituted. Instead of dH, instead of this dH, we have substituted TdS plus PdP. Okay. So dG equal to VdP minus SdT. The relation will be dou V by dou T at constant pressure will be equal to dou S by minus dou S by dou P at constant temperature. So these are the four Maxwell relations which has the relationship between pressure, volume, temperature with entropy and entropy, essentially, right? So what are the applications? So in chemical thermodynamics, they are used to calculate the equilibrium properties of chemical reaction and predict the direction of power, spontaneous change. For example, if you take internal energy, if the change in internal energy is negative, that is internal energy at start to internal energy at the end. If you minus, if it is negative, which means internal energy at the end is more, that is internal energy has increased. Similarly, in thermodynamics, they are used to design and optimize thermodynamic cycles, such as refrigeration, power generation cycles. In statistical mechanics, they are used to provide connection between macroscopic properties of the system and its microscopic components. Right? So we will see with another thermodynamic relation in next class. Thank you.